So here to tell us all about what the radio spectrum is Prashant Krishnamurthy from University of Pittsburgh. Thanks, and take it away.
Thank you, Maria. First of all, let me say thank you to Professor Zaleva and the Education Working Group. I see Anya is here. I don't know if it is here, but thanks to all of you for organizing the summer school. My name is Prashant Krishnamurthy. I am a professor at the University of Pittsburgh. The title of this presentation is "What is Radio Spectrum?" Although Professor Zaleva was very kind to say I'm going to say everything about the radio spectrum, it's probably not everything. You'll get the details as you go through the summer school. I know that you already have had lectures on wireless networks. So let me just say a little bit about myself, and then we can move on. So I'm from a department which is kind of different from most departments. It's called the Department of Informatics and Network Systems. We are in the School of Computing and Information at Pitt, but this department has an eclectic group of people. We have electrical engineers like myself. We have a lot of computer scientists. We have people who have PhDs in intelligent systems, which is like AI. But we also have people who work a lot on the human and social aspects of things. We have somebody who has a PhD from the Media Lab at MIT who does network science. So we have a variety of different people in this department, which provides a lot of broad perspectives on network systems and information science in general. As for myself, over the last 25 years, I have worked in wireless networks and security, and more recently in radio spectrum technology and policy, and a little bit of quantum networking that one of my students is doing right now. And within wireless networks and security, most of my previous work has been on localization and energy efficient security for wireless. That is my research side. As probably everybody can make out, I'm originally from India. I don't know if anybody can read this. This is the script of my language, which is Kannada, and it basically says my name is Prashant. And please stop me if you have any questions. I'm happy to answer as we go along. So today, I'm just going to talk a little bit about radio spectrum, and looking at the agenda, I think there are experts who are going to talk about things like remote sensing, radio astronomy, definitely about wireless communication, as well as spectrum sharing. I see Andy Clegg is here in the audience, and he's the expert on CBRS. But my goal today is to give a high-level overview of all of these topics. Think of this as a preview for what is to come during the summer school. So I'll talk a little bit about terminology, go through some of the uses and applications of radio spectrum, talk about the spectrum allocation process. Again, not in great detail, but enough so that you appreciate how these things happen, and also talk a little bit about rights and spectrum sharing. So first of all, let's ask, what is radio spectrum? Radio spectrum is essentially oscillating electric fields and magnetic fields. They create radiation that travels at the speed of light in free space, vacuum, which is 3 times 10 to the 8 meters per second. This number is extremely important because we use that all the time in wireless communications for determining the propagation delay, for understanding the relationships between frequency and wavelength, which are 2 important concepts when it comes to radio spectrum. The product of the frequency and wavelength is equal to the speed of light. So C is equal to F times lambda. Lambda is usually the wavelength, F is the frequency. So C is equal to F lambda, the equation that we use to translate between frequency and wavelength. In different applications, we see the use of frequencies and wavelengths. And so it's important for us to be able to make these comparisons. So what is frequency? Frequency is how many times the oscillations occur per second. And the unit of frequency is hertz. I'm sure that most of you are familiar with all the international systems of units, terminology like megahertz, gigahertz, and so on. So, but I assume that is the case, but if you have any questions, I'm happy to stop and explain. The wavelength is, if you look at the oscillations, what is the physical distance that one period of this oscillation, it repeats itself, how much is the physical distance between one repetition in meters? So these are the two numbers that are important when it comes to radio spectrum. So let's take a look at this picture. This is not visible light. I put the colors there just for illustration. It goes from the lowest frequencies, which if you see on the left, is around 3000 hertz, to the highest frequencies, which are 3 times 10 to the 12 or 3 terahertz. All of these frequencies correspond to the radio spectrum. On the top, you see the corresponding wavelengths. 3 kilohertz, roughly 100,000 meters. 3 terahertz is 0.1 millimeters. So the wavelengths range from hundreds of thousands of meters to lower than 1 millimeter. Frequencies, typically we look at kilohertz all the way to terahertz. And you can see the sinusoidal waveforms that I have shown here below. At lower frequencies, the spacing is larger of oscillations, whereas at higher frequencies, it's much closer. Again, this is not to scale, but just for illustration. If you look at the radio spectrum at different frequencies, their properties vary. And there is a lot of terminology here, much of which I don't myself remember. Often I have to look up the internet. But I thought that I will put some of this here just so that you're familiar with some of the terminology. For example, if you look at the table here, the frequencies are organized into certain categories. For example, 3 to 30 kilohertz is very low frequency. And 30 to 300 gigahertz is extremely high frequency. So in between, you have low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, and super high frequency. Again, these names may not mean much to you, but in the literature and when you look at radio spectrum, people talk about, oh, we are using the VHF for these purposes, or we use the millimeter wave bands for a particular application. And so it's important for us to be aware of what these things are. The properties are also different at different frequencies. At very low frequency, for example, the radio signals or the radio transmissions, they follow the Earth. It's called ground propagation. At medium frequency and high frequency, like AM radio, the signals can bounce off the ionosphere, which means they can travel long distances. You point the signal towards the atmosphere, it hits the ionosphere, and it can cross barriers and go very, very long distances. That cannot happen at other frequencies. Very high frequency is used for FM radio and TV broadcasts. And ultra high frequency is the frequency of interest to us a lot today, because these bands are often used for cellular communication, for Wi-Fi, for geolocation, and other things. Now, that doesn't mean that the other frequencies are not important. Many of these frequencies are used for radio astronomy, also for communications in the super high frequency range, for radar, and for many other different purposes. One thing I want to mention here is that the bands have other names too. And this is where things get confusing. You can see this. It's easy here to look at the adjectives like very, medium, super, extremely, and so on, and try to make classification for ourselves in our minds. But there are bands which are called by letters, and they don't have any specific, what should I say, simple way of recognizing which letter belongs to what. So I always get confused. We will talk about a couple of them later. For example, there is satellite communications today are using the KU and the KA bands, which you may learn about later. So I tried to create some nice images, but I kind of failed, and I resorted to AI to create a couple of images in my slides. So I hope you're all okay with that. So here is an image created by Copilot, which tells us the various places where we use radio spectrum. Communication, certainly. I already talked about geolocation a little bit. This is where I have done some research. But also for remote sensing, for weather radiometry, radio astronomy, and also inventory management, where we use RFID tags. Many different applications where we use radio spectrum. We see radio spectrum everywhere in our lives. I'll go through some of them in a little bit more detail in the coming slides. Also, radio spectrum is extremely, extremely important for critical use. Critical use meaning that these are for life-saving applications. For example, MRI machines, they use radio spectrum. But they use it for health reasons, for creating extremely detailed images of internal body structures, which we cannot get otherwise. X-rays are also a form of radio spectrum. Was there a question, or I'm not sure?
Sorry, we've got some noise leading through from the lobby.
Radio spectrum is also used, for example, in radio altimeters, where the pilots are trying to determine how high an aeroplane is above the ground. And this caused some policy questions, which, if time permits, I will show you a short video. Search and rescue beacons. If ships are at sea and they have problems, finding them requires the use of radio spectrum. And in disaster recovery, if there's an earthquake and you don't know if human beings are alive and buried under rubble, again, we need radio spectrum for finding these human beings and saving them. So many different critical uses of radio spectrum also do exist. So let me go over some of these applications in a teeny bit of detail. I mean, you will have presentations on communication, radio astronomy, remote sensing, and so on. I think 2 of them are tomorrow. So this is just a very quick preview, and I also don't claim to have great expertise in those areas. So you will hear from the experts later. In terms of communication, there are many different ways in which we can classify communication. I just picked a few here as examples. So communication can be unidirectional. So if you look at AM radio and FM radio, you get information, whether it is news, music, weather, traffic, in one direction. Some Internet of Things communications are also unidirectional. Only the sensors report to the base stations or the network. They don't themselves get any triggers unless they're actuators. Most other communications are bidirectional. So if you look at Wi-Fi, cellular, there's always something being sent from one device to another and the other device responding. This is one way of thinking about communication. Another way of thinking about communication is to look at the geographical coverage of the signals. So we have wide area, 4G, 5G, satellite, which cover large geographical areas, maybe the entire nations, parts of the globe. You also have local area, like on campuses, in your houses, where you use Wi-Fi. There's also personal area communication, which is, by one definition, around one human being. So you have your own personal devices, whether they are cell phones or headsets, cameras, other kinds of things, and then you try to connect all of them, for example, using Bluetooth. So these are 2 different ways of thinking about communication. I have some pictures here. You probably have seen some for cellular networks already. This is an example of a home network which has all kinds of smart devices, like a smart speaker, a smart switch, bulbs, all using Wi-Fi in this particular case. Internet of Things comes in many different flavors. For example, near-field communications, you can even have small stickers which can do near-field communications. You can, perhaps, if you're a football fan, Pittsburgh is a big football city. You go to the Acrisure Stadium, that is our stadium where the Pittsburgh Steelers play. Maybe you can go and look at the picture of the quarterback, scan your phone with NFC and download a poster. There are some symbols here on the slide. The green symbol here stands for a protocol called ANT, which is used for IoT. This is Bluetooth. And here I just put a picture of smart bulbs. Sometimes they connect using a protocol called Zigbee. Again, you may not remember all of these things because I'm going over all of them at rapid speed, but at least it gives you an idea, and you may look forward to some of these things in the later parts of the summer school. This is an old picture of a 2G wireless network. Probably can also be adapted for 3G. These are older networks which primarily were used for voice telephony. Today, 4G, 5G, and 6G networks are thinking more about all other kinds of data, not necessarily voice. And I'm sure everybody has heard about Starlink and Kuiper and all the other various satellite service providers which are trying to compete to provide communications, especially in remote areas where you don't have access to cell phone networks. There's a lot of interest today in the so-called direct-to-device communication, where satellites can directly talk with your cell phones. I think T-Mobile is working with Starlink to provide some of these services, and there are other competing services that will come up. The next application is positioning. Positioning also, to a great extent, includes navigation and also timing, because timing is extremely important when you want to locate a device. For example, in GPS, very fine-grained timing measurements will allow devices to figure out how far they are from 4 satellites. And if they know how far they are from 4 satellites, they can pretty much locate themselves with information about what these satellites are, because that information is known, where they may be located with respect to the Earth. And so you locate yourself. That is how GPS works at a very high level. And for measuring this time of flight, or how far away the satellites are from yourself, again, we use radio spectrum. So the GPS signals in the United States, they are the satellites that the United States has launched, they use frequencies in the so-called L band. As I mentioned to you earlier, this is not VLF, very low frequency, very high frequency, but this is a named band called the L band. And in this band, there are 3 frequencies in which GPS signals are transmitted. They go from 1176 megahertz to 1575 megahertz. I mean, they're not at all frequencies, but there are 3 specific bands, L1, L2, and L5, which I have listed there, which GPS uses in the satellites that the United States has launched. There are also satellites from other countries. Europe has its own system called Galileo. China, Russia, and India have also launched satellites which can help with geolocation. Together, we call this the Global Navigation Satellite System. And the satellites from Europe, China, Russia, and India do not necessarily use the same L band. Some of them use the L band, but they also use other frequencies, somewhere in the same range. And so radio spectrum is extremely important for GPS. Just last week, my family and we were on a road trip to Michigan to the Sleeping Bear Dunes. If you people have not gone there, then it's a very beautiful national park, worth visiting. My kids are 19 and 14, and my wife and I were telling them how we went when we first got married 25 years back to the same area. We didn't have GPS, we didn't have smartphones. They were saying, how did you actually get to this place? We were using standard old maps. Today we take GPS for granted, and it's because we have radio spectrum. Positioning can also be done using cell phone networks and Wi-Fi. There are many different techniques. The simplest one is to see which base station you are connected to, or to which Wi-Fi access point you are connected to, and you can pretty much say, okay, I'm within the boundary of the transmission of the base station or the Wi-Fi access point. GPS is also extremely important for safety reasons. The so-called aeronautical radio navigation service says extremely high safety requirements. These bands are protected because the L1 band in the US is protected, because we want to make sure that airplanes are safe. They can locate themselves, they know where they are, and we want to have high assurance that the flights are safe. Of course, this service also uses ground-based systems as well as GPS. So the next application is remote sensing. In remote sensing, there are two kinds, active and passive. In active sensing, a transmitter sends a signal and observes what is reflected back to make sense of the environment. In passive sensing, there's a natural radiation that is occurring that is being sensed. The big differences are, with passive sensing, we don't really have control. This depends on nature, what is being generated, more sensitive. In active sensing, we have some control over what we transmit and how we can change those things. Remote sensing is used for a variety of applications. Again, I'm not really an expert in this area, but I can mention a few examples, like forest cover, which uses visible light, not the radio spectrum. But for agriculture, for measuring the ocean salinity and temperature and sea ice, radio spectrum is used. These kinds of measurements are useful for forecasting the weather, for farmers to figure out when there might be a drought and make preparations for that, and so on. There are many satellites that both the US and Europe have launched for remote sensing. I have two examples here. The first one is Europe's soil moisture and ocean salinity project, which is measuring, as the name suggests, soil moisture as well as ocean salinity. NASA's soil moisture active passive uses both active measurements and passive measurements to look at the soil moisture. Just a couple of months back, the Indian Space Research Organization, working with NASA, launched a satellite called NISAR. This combines the L band that NASA uses, and ISRO, the Indian Space Research Organization, is using the S band, which is between 2 and 4 gigahertz, if I understand correctly, to detect changes in land and ice, if the coastal boundaries are shifting. And my understanding is that they can even measure these things up to the centimeter level, which is impressive considering that these measurements are being done from space, again, using radio spectrum. Radio astronomy is probably a little bit more familiar to folks because many of you might be familiar with the SETI project, searching for extraterrestrial intelligence, listening to signals from outer space. The bands are wide. Measurements can be taken at almost every frequency in the radio spectrum. And there are some important differences. There are continuous spectrum measurements. There are also spectral lines, which are important because they allow us to detect specific molecules and chemicals in distant bodies. Last year, I think there was an article that I saw where some black holes were detected using radio astronomy. NSF has a report on that on their webpage if you're interested in looking at it. The problem with radio astronomy is that the signals are coming from, I don't know, maybe light years away, which is very, very long distances. And so the signals are extremely weak, and human-generated signals on the planet will interfere with those signals. And this can happen, and even very, very low levels of radio signals that we generate could mask what we would like to detect from outer space. For protecting against these kinds of even accidental interference from human devices, there are many strategies that can be adopted. One of the strategies is to create a radio quiet zone about a little bit more than 10,000 square miles in the states of West Virginia, and Maryland has been classified as a national radio quiet zone. Most wireless devices are not allowed within 10 miles of a couple of observatories which are there, one specific to the National Security Agency, but other one which is looking at radio astronomy. And so in these areas, you cannot get Wi-Fi, cell phone, or any other kind of wireless service, and you're not allowed to use those devices as well. I just will stop sharing this and share a web page, just so that I just want to point to a couple of interesting things here. So this is from the NASA website. It's called earthdata.nasa.gov. Here they have a bunch of instruments that they have deployed for collecting Earth science data. I'm not going to go through all the 20 pages of things that they have. They're really interesting things. For example, if you look at this advanced microwave radiometer, can people see this?
Yes.
You see, it is using brightness temperatures at various frequencies in the radio spectrum. They have data sets, things that might be interesting to people. Get back to my presentation. So, okay, we know something about the radio spectrum. So we have this entire range of frequencies, that you see here, from 3 kilohertz to 3 terahertz. It's common for us to think of these as boxes. So you can think of there's a box here, there's another box here, and we are separating these frequencies into these boxes. And we can give different boxes for different applications. So we have the L band, which is used for GPS. We have some other frequencies which are used for 4G networks, maybe some frequencies that are used for Wi-Fi and so on. But it's not that simple, because these boxes are not, nicely bounded. Really, what we are interested in is something called the power spectral density, which is roughly, as the name suggests, how much power is there in a unit of frequency. And this power is not bounded in frequency. It is actually, it leaks everywhere. And out-of-band emissions can cause interference. So interference is a topic that we will talk about a little bit in the next few minutes. So before we do that, let's talk about one of the common confusions that people have is between bandwidths and data rates. And we try to conflate the two of them. We say bandwidth and data rate are the same, but they're not really the same. Bandwidth is related to the radio spectrum. Data rate is what is the bit rate that you get. Of course, there's a relationship between the two, but they're not exactly the same. So when we talk about bandwidth, we are talking about frequencies that are filled up by a signal. And what do we mean by filled up? So here's a picture. Again, I'm not getting into the nitty-gritty details here. On the x-axis is the frequency, and on the y-axis is the power in a signal. This is a signal that we have kind of translated into the frequency domain. So the signals are transmitted in time. You look at the frequency components in the signal, you can say, okay, there's a lot of power in the middle here. The power is degrading as we look at other frequencies beyond this middle frequency. But if you look at the total power in the signal, and one of the definitions that people use is that we have 99% of the total power is contained within a set of frequencies. And that set of frequencies, for example, could be a box that we put there. This is definitely not 99%, but just for illustration, we say that is the bandwidth of the signal, which is B hertz. So bandwidth is measured in hertz, data rate is measured in bits per second. But clearly you can see that there is power beyond this box. And this power causes interference to the neighboring bands. And so that is something that we should all appreciate when we look at radio spectrum, because radio spectrum cannot be nicely bounded in frequency. And this bandwidth B is what is allocated. When we look at spectrum allocation, for example, this band, I just made this up, might have been allocated for mobile satellite applications. The next band, which starts here and goes beyond, is allocated to amateur radio and so on. But we know that there is some leakage from the mobile satellite signals into the amateur radio band and so on. Again, I will stop here for 1 second, sharing. And this is something that you probably, somebody might have already shown you, but I'd like to just bring this up for the sake of completeness. This is the 2016 US Department of Commerce NTIA's picture, very famous PDF of the allocation of radio spectrum. You can see that it goes somewhere here from 9 kilohertz, I think, if I can read it properly. See if I can zoom in. Yeah, from 9 kilohertz all the way to 300 gigahertz. This is the allocation that has been done. You can see that it is full. You don't see any white rectangles here. Some of these have changed a little bit here and there, but almost every frequency here has been allocated for some purpose or the other, whether it is radio navigation, whether it is broadcasting, whatever the application might be. Have you all seen this chart before? Just a show of hands, maybe?
Okay.
No?
Very few.
I'm sure that somebody will show this to you again.
No, I don't know, Bonnie. Not yet, anyway.
We'll bring some hard copies for them to see.
So this, we talked about interference, and I think I talk a little bit more about interference. Football analogy here, again, image created by Copilot. Here, the referee is interfering with the football instead of the players. When we use radio spectrum, we use radio spectrum in space, which is geographical area where the spectrum is being used. In time, when is it being used? If you use it today and don't use it for the rest of the year, okay, that spectrum is free from tomorrow. Frequency, we talked, which is the boxes that I just showed you. What are the frequency ranges that we are using, for what purpose? Who are the neighbors? How are they using their frequencies? If it is active, where we are transmitting something and receiving something, what is the transmit power? If it is passive, we have other problems, which we will talk about a little bit later, if you have time. And whether there is technology that we can use to mitigate the interference. In cell phone networks, there's a variety of technologies that we are using. Interference cancellation, adaptive antenna arrays, and many other different AI these days, machine learning to mitigate interference. It's more difficult to do it across different applications. Long story short, I wanted to show this video. Maybe I will show it and I'll skip the last video if I don't have time. A couple of years back, in the upper 3 gigahertz bands, they were allocated for 5G services. And the neighbors for that band were the radio altimeters that we talked about, where the airplanes use the radio signals for estimating the heights. And so there was this challenge that came up, whether there's interference between 5G signals and the radio altimeters that the planes are using. There was a lot of angst, policy debates, questions about what should be done, whether they can actually be used safely. So let me just show you this video from the Wall Street Journal, which talks about this problem.
Prashant, if you can just make sure that you're sharing your computer sound to Zoom as well. When you click on share,
Okay,
There should be an option to share computer sound too.
I see. Share sound. Okay.
Okay.
Just give me 1 minute. In order to do that, I am supposed to give my administrator password.
That might ask you to restart your Zoom connection.
Okay, so maybe we will skip this the video, and I will just send you the link is there. If you're going to share the slides, I think people can watch the video. It's not very long, but it gives you an idea of and it has a short interview with one of the people.
That's great.
So I will just go back to sharing my presentation. So another consideration when it comes to interference is the importance of frequency and propagation. And I'm not going to spend too much time on this slide. The x-axis here in the plot shows the distance in meters. The y-axis shows how much is the loss in the signal strength in dB if we assume free space propagation. Of course, we cannot assume free space propagation everywhere, but this is just a benchmark if you want to think of it that way. As you see here, as the frequency increases, the loss in the signal strength as a function of distance is also proportionally, I mean, it's not proportionally, but it is larger. And there are some specific effects at different frequencies, like there's oxygen absorption in 60 gigahertz. In 2.4 gigahertz, you have water vapor. Water absorbs the signal. And there are some natural phenomena which only radiate signals in certain frequency bands. So there are some frequency considerations when we look at interference as well. In general, the larger the frequency, the greater is the propagation loss. And so if you're having a fixed transmit power, the interference range is also smaller. So these are the considerations that we have: space, time, frequency, power, and technology. And we look at interference, and these are used in making allocations in some ways, regulations, perhaps not allocations. Allocations are a much more political and deliberative process. First of all, there's an international process where the ITU-R, which is the International Telecommunications Union, R, does some high-level allocations. There are many regions in the map, and each region might have a difference in where radio spectrum is allocated. There is a WRC, World Radio Communications Conference, that is held every 3 to 4 years. It's a treaty-making conference. It's very long. It takes a lot of time for spectrum to be allocated for an application. For example, for GPS and GNSS, a lot of deliberations happened in 2000 and 2003 for the allocation of spectrum. The last World Radio Communications Conference was held in Dubai a couple of years ago. Big focus was on satellite use. But the next World Radio Communications Conference will be held in China. And among other things, there will be some discussion of IMT, which is 6G in WRC 2027. There are many other topics that are discussed, and the FCC contributes to this process. They have informal working groups. They have other kinds of deliberations that happen in the US. And then the US provides its position, other countries provide their position, and eventually there is some kind of an allocation that is agreed upon and made in these meetings. Within the United States, Congress makes all decisions, essentially is in control of all decisions related to the radio spectrum allocations, but this is delegated to the FCC, which is the Federal Communications Commission, and in a different manner to the National Telecommunications and Information Administration. The FCC looks at non-federal use of radio spectrum, which means if the spectrum is allocated to an agency that is not a federal government agency, then the FCC is responsible for regulating that. There was auction authority that the FCC had for a long time to auction spectrum for cell phone services, for example. It lapsed. Now, in the recent bill that was passed, it has been renewed. The NTIA, the National Telecommunications and Information Administration, it manages the federal use of spectrum. So it looks at the spectrum that the Department of Defense, the Federal Aviation Administration, Department of Energy, NASA, and everybody else, the federal agencies are using. They work together to investigate new uses of spectrum. There has been, in the last couple of years, many examples where they have worked together to do different things with spectrum, which would not have otherwise been possible. Now, the FCC itself has a rulemaking process. It's a long process. Either the FCC, because there are very capable people there looking at the usage of radio spectrum and the national needs and so on, or industry and other parties can decide to think about a particular problem. So it could be an external petition, or the FCC does it itself. And they have a notice of inquiry where they're asking people, okay, this is what we are thinking, and what do you people feel? So the idea behind the notice of inquiry is to generate ideas, to generate ideas about this proposal. So let's say there's a particular radio spectrum slice, and they think that it can be better used or it can be used differently. So these are the possibilities, and what do people think? And there are lots of comments and responses that people send to generate the ideas. Once the ideas are there, the FCC looks at those ideas and issues a notice of proposed rulemaking. It says, okay, we are thinking of making this rule. What do you folks say? So stakeholders, they submit their comments. People read the comments, and the stakeholders may say, okay, the other person said this, so here is my response. So there's a reply comment. Then there is a further notice of proposed rulemaking. FCC looks at all of these documents, and it can change the rules a little bit, tweak it. Maybe it says, okay, we will try something different. And finally, there's a report and order, right, once a final decision is made. Some of these things may be iterative. They may not happen in a single shot. And it's not exactly one piece of radio spectrum that the FCC looks at a time. There may be many things happening in parallel. Many of these documents are public. My colleague and I, for example, we looked at some of these comments and replies related to CBRS, and there's a citation here for that work. And when the FCC makes allocations to spectrum, and the allocations are there, it's for a particular use, but who gets the spectrum? And so are there any rights to the spectrum? So do I get to use the spectrum? Does a different company get to use the spectrum? These are all questions that come up. In the early days of radio spectrum assignments, it was centralized. The regulators made the decisions. I will give you an example. But over time, there were arguments made by two Nobel Prize winning economists. Ronald Coase said that spectrum is like property, and so it can be sold. Now we have auctions for radio spectrum. There's also a so-called Ostromian view, which is that spectrum is maybe like property, but it is also a shared property. It's like a commons. There are multiple users, and users need to negotiate. This works very well for active users, where we can regulate the transmit power. We can say who can use the spectrum where, but this causes significant challenges to passive users. For example, if you're doing radio astronomy, the radio quiet zone is important. Otherwise, there will be too much interference from human transmissions. People also talk about this as a landscape right, because if you look at wildlife, has no boundaries. They don't respect property boundaries. They don't say, okay, this is your house. I'm not going to, the deer in the place where I live, They don't care whether it's my house or my neighbor's house. They come and eat all the plants, and they roam everywhere. And so this is a similar situation with some passive users of radio spectrum. They span many different bands, and some bands have certain regulations, other bands have other regulations, and we cannot necessarily respect those in the same way when we are looking at passive users. I'm not going to go into all the details. In 1G, which is in the 1980s, spectrum allocation was done through command and control. There were some comparative hearings and some lotteries, and they allocated the spectrum. In 2G, in the 1990s, they used auctions to assign the rights to spectrum. And spectrum has become extremely valuable. This is not in the US, but in the UK in September 2021, the cost of 200 megahertz of spectrum in the 3.5 gigahertz bands, which is used by 5G, was about 1.4 billion pounds. I think a pound is like $1.20 or something these days. So you can make the calculation. It's about $1.5 billion or more for 200 megahertz of spectrum, which is really expensive. We also have unlicensed spectrum. This is not spectrum that is auctioned. Wi-Fi, for example, Bluetooth, garage door openers, many other applications, they use unlicensed spectrum. And some people have in the past compared unlicensed spectrum to backyard barbecue versus public space barbecue in the park. Typically with unlicensed spectrum, we have some kind of an etiquette. So you can't willy-nilly do whatever you want, but there are some regulations on what is the transmit power you can use, what are the protocols that you can use, whether you need to maintain some level of interference to your neighbors and so on. Ultra wideband, which is what is used in AirTags, if anybody has AirTags with iPhones, that is an extremely wideband unlicensed spectrum, but it has a low power spectral density. So the power is very, very low and hopefully will not interfere with other signals there. Recently, there has been some interest in sharing spectrum. As you saw the spectrum allocation chart that I showed you, all the spectrum has been filled. It has been allocated for something or the other. So what do we do for new applications? What do we do for new demands that may come up? Technology is changing. We can do new things when it comes to things like radio astronomy or weather radiometry or communications. There's a lot of demand for broadband communications. So what do we do? So one idea is maybe there are some allocations and assignments that are not efficient. When we say efficient, there are different metrics. There are economic efficiencies that you may learn about in a different lecture. There are usage efficiencies like utilization, whether spectrum is actually being used or not. One example, in the 5 to 6 gigahertz bands, in some of those bands, there were point-to-point microwave links. They were used, but they were sparsely located in geography. So they were not used everywhere. So the FCC, for example, has allowed some unlicensed use of this band with some restrictions, which is that if you're using very low power, you can use it everywhere like ultra wideband. It's not exactly the same, but similar in concept. You can use low power in indoor areas because you're not going to interfere too much with the microwave links. But if you are using high power, slightly higher power outside, then you need to have some databases. They call it automatic frequency coordination to make sure that you're not interfering with these microwave links. There is also a lot of interest in sharing in the federal bands. CBRS is a good example of this. I'm going to go through this quickly because I know you have a lecture on CBRS later. CBRS is between the 3.55 gigahertz and 3.7 gigahertz bands. Within the first 100 megahertz, there are 10 megahertz channels. These channels can be licensed. There are some restrictions on what the licenses can be. In the remaining 50 megahertz, you have unlicensed access. What CBRS does is that it uses a database and some sensors to detect the activity of Navy radars to decide whether transmissions are allowed. And it's a very complicated process. And what I'm telling you is only very, very high level view of CBRS. But but it is an example of sharing with federal systems. Recently, the FCC has a notice of rulemaking trying to make some changes to CBRS. There were a lot of interesting questions that were asked in this notice of rulemaking. My colleague and I, we did an analysis of the comments and the reply comments, and what we found out was that most people were interested in looking at the increase in transmit power. CBRS, because it is sharing spectrum with federal incumbents, cannot transmit at power levels of cellular services. So one of the questions that was asked, or even if it was not asked, people responded about that question, is whether they should allow increasing the transmit power. And there were a wide variety of comments. For example, all the red bubbles that you see here, they were the people opposed to it. The cellular service providers like Verizon and so on, they were actually in favor of Ericsson, which is a vendor for cellular equipment. They were kind of in support of increasing the power. There were some neutral people as well. And we did this in a subjective way because this is not an objective evaluation of the comments and the reply comments. This is a video that I want to show. Hopefully I can show it because it's embedded in PowerPoint.
Please, sir. I want some more.
Can people hear that?
What? Some more? Some more?
Can people hear that?
Yes, it's coming through.
So that's from Oliver Twist, where Oliver Twist is asking for some more. But I think the challenge for us today is that we all want more spectrum. It's an interesting problem when everybody wants spectrum. Spectrum is an important resource. It has uses in, really a large number of applications. Demand for spectrum is only increasing. It's extremely important for the nation, for its economy, for a variety of new applications. And so we really need to see how best to use this important resource. There's another question that comes to my mind, which is that in the future, perhaps there will be more machines that spectrum than human beings with the emergence of robotics, AI agents, and so on. Only time will tell us how we will be using spectrum in the future. That is all I have to say today. I have to give credits to a lot of people. And I could not put all of their pictures here. I put some of the more people who are closer to this presentation. Professor Monisha Ghosh from Notre Dame, Professor Ilya Murtazashvili from Pitt, Professor Martin Weiss, who's my colleague in my department, Professor Michael Honig from Northwestern, and many others, many of my advisors, my students, colleagues at SpectrumX and elsewhere, helped me understand the wireless world, the point where I am today. So I have to give them credit for all of this. So that's all I have to say, and I'm happy to take any questions.
Thank you, Prashant. Yeah.